Now, without actually writing the molecular orbital configuration, let us see which is para, which is dia, which is paramagnetic, and which is diamagnetic. There is a simple principle in which you have only one capital letter, and no number. No unpaired electron. If there is no unpaired electron, it is dia. Yes, unpaired electron. If there is an unpaired electron, it is para. And copper is an exception. I will tell you what I mean by one capital letter. That is what I mean by element or elemental ion, Na plus, like that. Okay. Na, 3s1, unpaired electron is present, therefore para. Sodium is paramagnetic, sodium atom is paramagnetic, like that. Al plus, aluminium plus, one capital letter, oh, you have only one capital letter, it is an ion, element, elemental ion. If you write down the electronic configuration, it is 12, 1s2, 2s2, 2p6, 3s2, the last electron is 3s2, no unpaired electron, therefore it is dia. All are paired electrons. So, no unpaired electron, therefore dia. So, Al plus is diamagnetic. What about copper? Cu, 3d10, 4s1. It has an unpaired electron, but still it is diamagnetic, because you have 5 pairs of electrons versus one unpaired, and this diamagnetic property dominates in copper. And this is for more than one capital letter, in which you have more than one capital letter and a number, in which you have a number. Total number of electrons, you count the total number of electrons. Odd number, it is paramagnetic. Even, it is dia. Total number of electrons, odd, para, even, dia. O2, B2, N2, 2 minus, and S2 are exceptions. Let us see what do you mean by that. CO, carbon monoxide, is it paramagnetic or diamagnetic? You just count the total number of electrons. Carbon atomic number 6 plus oxygen, 6 plus 8, 14, even, therefore dia. NO, 7 plus 8, 15, 7 plus 8, 15, it is odd number, therefore it is paramagnetic. Like that, CO, NO, you can find it anybody, O2 plus. So, there are two rules. Here you have two capital letters, means I do not want to call it a compound, because CO is a compound, NO plus is, strictly speaking, is not a compound, NO plus is an ion. So, let us apply in more cases. Mn2 plus, is it a one capital letter case or more than one capital letter only? Manganese, elemental ion, because strictly speaking I can't call this as elemental ion, it is a compound ion formed from a compound, NO plus. Therefore, this is formed from an element only, one element only. Now, Mn2 plus, what is the configuration? 3d5. Manganese, it is argon, 3d5, 4s2, When you remove these 2 electrons, you will get Mn2 plus. Mn2 plus 3d5. So you have 5 unpaired electrons, and therefore it is paramagnetic. And NO2, it is not one capital letter, more than one capital letter. When you have more than one capital letter, add all the electrons. 7 plus 16, 23, odd, therefore para. NO2 is paramagnetic, NO is paramagnetic, CO is diamagnetic, O2 plus is paramagnetic, O2 plus, 8 plus 8 minus 1 electron. Here is a number, number means 2 atoms more than O2. So 2 oxygens removing 1 electron, 8 plus 8 minus 1, 15, odd para, like that. But what about O2, B2, etc.? O2, B2, they are paramagnetic even though the total number of electrons 8 plus 8 is 16, even as an exception, because even but para, you know the reason. The 15th, 16th electrons are unpaired electrons. 15th and 16th they enter unpaired. They enter PXY, they are and 15th and 16th enter equal energy electrons, equal energy orbitals, therefore they enter one after the other. So O2, B2, N2, 2 minus, once again 16 electron system, B2 is 10 electron system, 10, 16 or even but para. Now, the last thing to both periodic table and which involves periodic table and chemical bonding also is oxidation states. All about oxidation states. Actually, we could have studied this in periodic table itself, but since it involves a little bonding also, I have brought in that here at the end of both the chapters. Now, what is this oxidation state at all? This oxidation state is the charge, real or imaginary, sometimes real, sometimes it is imaginary, real or imaginary. How is it calculated? Calculated by attributing all the electrons in a bond, whether they belong to the other atom or this atom. HCl, there are 2 electrons, one of them belongs to H, but still we attribute both the electrons to all the electrons in a bond to the more electronegative atom. So why did I say real or imaginary? What is the definition of oxidation state? Charge acquired by an atom. It may be real charge or imaginary charge. Charge acquired by an atom in a group, whether it is real or imaginary. How is it calculated? It is calculated by attributing all the electrons to the more electronegative atom. Look here. And you know which is more electronegative. Behind all this electronegativity order, electronegativity of fluorine greater than, oxygen greater than, nitrogen greater than chlorine, this holds good. H greater than, B greater than, and you know you get other non-metals here. Now, CH2O. What is carbon doing here? Carbon is in fact forming 4 bonds. You can say the covalency of carbon is 4. Covalency, number of bonds formed, 4. So, carbon forming 4 bonds can be compared to carbon playing 4 matches. Carbon is playing 4 matches, 1 match, 1 match, 2 matches with oxygen. So, what is it? Net tally? In some matches it wins, some matches it loses. When do you win? When do you win in general? When you play a weaker team you win, when you play a stronger team you lose. So, oxygen being stronger, these 2 matches are won by oxygen. So, I say the score of oxygen is -2. Those 2 bonds are put into the account of, all these electrons put into the account of oxygen, minus 2. Means even the electrons of carbon also are also taken into the account of oxygen. Oxygen is winning the electrons. It's like winning a match. And hydrogen, carbon, technically carbon is more electronegative than you, since you have other here bromine, iodine, carbon, sulfur, phosphorus, etc. are here. So hydrogen theoretically loses this match. So what is carbon doing here? Winning 2 matches against hydrogens and losing 2 matches to oxygen. Net oxidation state is 0. So carbon is forming 4 bonds, but 2 of the bonds with less electronegative and 2 of the bonds with more electronegative. Net happens to be a loss of 2 electrons and a gain of 2 electrons. Net is 0. That's it. So it's all very difficult to write down the structure every time and calculate. Therefore, we need to have a procedure. So what is the oxidation state of phosphorus in its compounds? Oxidation state of phosphorus in its compounds. In its compounds, we can't say. Why? Because phosphorus forms several compounds. In pH3, it is minus 3. The oxidation state of phosphorus is minus 3. Because phosphorus is forming 3 bonds with 3 less electronegative hydrogens, hydrogens which are less electronegative than phosphorus. In PCl3, chlorine being more electronegative, the electronegativity is plus 3. In PCl5, it is plus 5. So sometimes minus 3, sometimes plus 3, sometimes plus 5, sometimes it may be plus 1 also, sometimes 0 also. When it is forming bonds with equal opponents, PP bond, it is 0. Therefore, you just can't say, if I ask you what is the oxidation of phosphorus, it varies. It varies. But what is the oxidation state of potassium in its compounds? Potassium in its compounds. Now, you need not say it varies or it depends on which compound it is, because in all compounds of potassium, potassium is always plus 1. So it is fixed. Some elements have fixed oxidation states, whereas some elements don't have fixed oxidation states. So let us first draw the rules. Which elements have fixed oxidation states? Fixed oxidation states. 1A, elements of 1A, lithium, sodium, potassium, etc. Their oxidation states in all compounds is always plus 1, fixed, that way they will never vary. 2A, beryllium, magnesium, calcium, etc. always plus 2. And fluorine always minus 1. That's all. And of course, there are 1 or 2 others like aluminium always plus 3, zinc always plus 2. But let us not make this list too long. First, realize that certain elements have fixed oxidation states, whereas certain elements don't have fixed oxidation states. It's enough if you know certain elements can have fixed oxidation states, certain elements will not have fixed oxidation states. 1A, 2A, fluorine, and a few others. Don't make this list too long, is a warning here. Now, this is the first rule. Second, maximum oxidation state. Maximum oxidation state of an element is equal to its group number. The chief exception being copper. And when I say group number, it is Mendeleev's group number, it is not the IUPAC group number. IUPAC group number is not very much useful. If I say chlorine belongs to 17th group, that doesn't help us much. The group number 7, the old notation 7A of manganese is more useful to us. I mean, Mendeleev is more useful to us. Copper belongs to 1B, but its maximum is plus 2. So, to some extent, copper, iron, oxygen, fluorine, they are not much of an exception, because iron belongs to the 8th group, it is permitted to exhibit plus 8, but it doesn't exhibit. So, that is, if it crosses the limit, then you can say it is an exception. So, maximum group number, maximum oxidation state cannot exceed group number. So, oxygen can exhibit up to plus 6, but it does not exhibit, that is a different matter. But copper is definitely an exception, because copper belongs to 1b and it cannot go beyond plus 1 according to this rule, but copper indeed exhibits plus 2 oxidation state. Now, maximum oxidation state. Minimum oxidation state is equal to group number minus 8. Group number minus 8. This is for 4A to 7A groups only. 4A to 7A only. That is from carbon to fluorine groups. 4th group, 5th group, 6th group, 7th group. What about all other groups? You have first group, second group, D block, 10 groups in D block. What about their minimum oxidation state? Before 4th group, aluminium, gallium, indium, thallium, etc. all other elements, S block, D block, F block, the 2 groups of S block, the 10 groups of D block, the 14 odd groups, if you do not want to call them groups, series, 2 series, F block, and even 3rd group except boron, all others are metals. All these are metals, and you know metals can never exhibit negative oxidation states, therefore 0. So, it is enough if you have a rule from 4A to 7A. Noble gases, any case, they do not exhibit any compounds, therefore theirs is also 0. They do not have a maximum or they do not even have a minimum. So, maximum oxidation state is equal to group number, minimum oxidation state is equal to group number minus 8. So, sulfur, what is the maximum? 6th group plus 6, minimum 6 minus 8 minus 2. Chlorine, 7th group, maximum plus 7, minimum 7 minus 8 minus 1. Phosphorus, maximum plus 5, minimum 5 minus 8 minus 3. Carbon, 4th group, maximum plus 4, minimum minus 4. So, all these elements can exhibit any oxidation state, Now, the third and the last rule. First rule is about fixed oxidation state, second rule is about maximum minimum. Third one, if oxygen is O2 minus, then the compound is called oxide. If oxygen gets an oxidation state of minus 2, if oxygen gets minus 2, then it is oxide. If oxygen gets 2 minus, is called an oxide. If oxygen gets O2 2 minus, what do you mean by O2 2 minus? 2 oxygen atoms getting 1 electron each, that is 1 oxygen getting that is equal to O minus, or oxygen single bond. Whichever compound you have oxygen single bond, that is called a peroxide. If oxygen gets minus 2, it is an oxide. If an oxygen gets minus 1, it is a peroxide. And if oxygen gets minus half, that is O2 minus 1. Here 1 oxygen gets 2 electrons, here 1 oxygen gets 1 electron, here 1 oxygen gets half electron only, or oxygen minus half, O minus half, it is called a superoxide. There is the matter. If oxygen gets is the word I have been repeatedly using. If oxygen gets, it does not depend on what you give to oxygen. What oxygen gets is what matters. What oxygen gets by virtue of others. Now, what is the name of KO2? Depends, the name of oxygen compound depends on its oxidation state, KO2. What do you know about K? First group, potassium, fixed. So, potassium is always plus 1 and 2 oxygens together minus 1. each oxygen minus half. So oxygen got minus half because potassium is willing to lose only one electron. It doesn't give more than one electron. Therefore, it is potassium superoxide. Why is it a superoxide? Is it because I have given minus half to oxygen? No, because oxygen got minus half, mind you. I haven't given anything. Oxygen got it by virtue of its bonding with potassium. Potassium says I will give one electron. Two oxygen says okay. Two oxygens agree to take one electron. Potassium superoxide. What will be the name of BaO2? What do you know about barium? Is there any fixed element or not? First of all, you tell yourself whether there is a fixed element or not. Barium fixed plus 2. Two oxygens minus 2. So, each oxygen is getting minus 1, minus 1. So, when oxygen gets minus 1, it is called a peroxide. Therefore, it is barium peroxide. Barium peroxide. So, whenever there is an element with fixed oxidation state, that element will take charge of that molecule and decide the oxidation state of others. He will take in charge, he will become the owner of that molecule and he will decide others what others should get. Now, BaO2. In the absence of fixed oxidation state, in the absence of fixed oxidation state, give minus 2 to oxygen. In the absence of fixed oxidation state, give minus 2 to oxygen, and if the other atom gets impossible oxidation state. When there is no fixed element, what do you mean by that? No 1A, no 2A, no fluorine. When they are not there, when they are there, there is nothing for you to worry. They will decide others. So, in the absence of fixed oxidation, you give minus 2 to oxygen. If the other atom gets impossible oxidation state. What do you mean by impossible? Higher than the group number. Higher than the group number, then it is a peroxide. Means oxygen becomes minus 1. If oxygen is minus 2, others are becoming 2 plus, too much, too high positive charge. Therefore, oxygen says minus 1. If oxygen takes 2 electrons, others will become highly positive. When they become highly positive, impossible, higher than their group number, then oxygen says okay, minus 1, it will decrease. So, oxygen is variable here. In all the compounds, oxygen is variable. Now, so what is that you should see? Whether there is fixed or not. Only one step. Fixed oxidation state or not. If fixed is not there, give minus 2 to oxygen. Then decide others. Sir, what if fixed or oxygen are not there? Okay, we can come to that. That's not a very important thing. But most compounds we have to find in which oxygen is involved or oxygen is not involved. Now, MnO2, is it a peroxide or a dioxide? How can you find out? There is no fixed. Therefore, give minus 2 to oxygen, minus 4. Manganese gets plus 4. Is plus 4 okay for manganese? If plus 4 is okay for manganese, oxygen can always take minus 2. Therefore, it will be an oxide. Oxygen need not change its position. Oxygen need not say okay. So, manganese says no problem for me. Why? Manganese belongs to 7th group, plus 7. Highest oxidation state is plus 7. Minimum, of course, metal 0. 0 to plus 7, manganese can take anything. Therefore, manganese plus 4, no problem. Therefore, oxygen, giving minus 2 to oxygen here is not wrong. So, therefore, it is an oxide. Here it is okay. Stick mark means okay for manganese. Okay. Manganese says okay. And this is not a peroxide. Not a peroxide. This is not a peroxide, this is a normal dioxide. This is a normal dioxide. What about NO2? Is it a dioxide or peroxide? Long ago, it was by mistake called nitrogen peroxide, but no longer it is called peroxide, it is not a peroxide. Now, -4 plus 4. Plus 4 is okay for nitrogen. How? Nitrogen belongs to fifth group. Anything from -3 to +5 is okay for nitrogen. +4 is okay. Therefore, oxygen is -2. It is not a peroxide once again. Not a peroxide. Not a peroxide. What is the name? Manganese dioxide, nitrogen dioxide, carbon dioxide. PbO2. It was also called lead peroxide. In the old it was called lead peroxide, but it is not a peroxide. Strictly speaking, it is not a peroxide. Because if it is a peroxide, it contains oxygen-oxygen single bond. There will be one bond between oxygen and oxygen. Okay. PbO2. Give -2 to oxygen, -4. Lead, +4. Okay, because lead belongs to fourth group. Lead being a metal, 0 to +4 okay for lead. 0 to +4, anything okay for lead. Therefore, +4 is okay. Therefore, once again, not a peroxide. Not a peroxide. So, what will be the name? Lead dioxide. Lead dioxide. Like carbon dioxide, lead dioxide, silicon dioxide, germanium dioxide. Like that. But look at CrO5. CrO5. Can I call it chromium pentoxide? Can I say all of them are oxides with -2 oxidation state? -2, perhaps no. Let us see why not. -10, +10. Can it take chromium take +10? Oh my God, impossible. It's not saying okay. Until now everybody is saying okay, okay. But this is not okay. Chromium says, sir, I can't afford 10 electrons because chromium belongs to sixth group. 0 to +6, anything okay for chromium. +3 okay, +4 okay, +6 okay, but not +10. Therefore, what is that oxygen should do now? It should decrease its level. Instead of asking 2 electrons, it should satisfy with 1 electron. Now, so, see how to draw the structure, we all know. How to draw the structure? 1 chromium, 5 oxygens, and we know this fellow has got a peroxy bond also. How do you know peroxide is a peroxide? Because chromium getting impossible oxidation state, it is a peroxide. Therefore, oxygen-oxygen single bond is there. What do you mean by peroxy? Oxygen-oxygen single bond. Be specific about that. Oxygen-oxygen single bond. Now, oxygen forms 2 bonds. Oxygen forms 1 bond, 1 bond, 1 bond, 1 bond. And chromium cannot play any more matches. Chromium has 6 electrons only and it is playing, forming all 6 bonds. So, what else is needed? These 2 oxygens need 1 more bond. So, they take a bond between them. What is it we have got? We have got a butterfly structure. Many books draw the structure first and teach you oxidation state like this, but it is not way. From oxidation state to structure, it is not from structure to oxidation state. If that is the case, how many structures you can remember? That is why people think that chemistry there is a lot to memorize, whereas there is not at all. That is not true. Follow a principle. What is the principle? You give -2 to oxygen. If the other atom says yes, okay, it is an oxide. And moreover, you see, it can afford only 6, but oxygens need 10. There is a difference of 4. Means 4 oxygens should decrease their demand. Instead of asking to give 1 electron, we get 1 electron from somewhere. Oxygen needs 2 electrons, no doubt, but from chromium they take 1 each from chromium and 1 each between themselves, and the resulting structure, it looks like a butterfly. So, we in fact have drawn the structure from oxidation state. Oxidation state to structure. It is not structure to oxidation state. You should observe the difference. If you start writing structures and then find oxidation states, it will become too difficult. because you should learn all structures before you start writing oxidation states. CrO5. So, number of peroxy bonds is equal to number of peroxy bonds. You don't need much of a formula. It is a common sense. It's common sense. The demand made by oxygen is for 10 electrons. The demand chromium can meet is 6. So, oxygens must look out for 4 more. So, impossible oxidation state, whatever impossible you have got, minus maximum oxidation state by 2. That is CrO5 plus 10 minus 10. This is impossible. 10. Maximum is 6. 10 minus 6 by 2. There are 2 peroxy bonds. That way you have got 2 oxygen single bonds. Now, H4P2O7. Do you have a peroxy bond in this? H4P2O7. H4P2O7. Do you have a peroxy bond? In the in the previous part, we have even discussed how to draw structure also. I taught you 2 phosphorus atoms, 4 OH groups, 4 OH groups. How do you know the number of OH groups? The number of OH groups is equal to number of hydrogens present. If you have 4 hydrogens, 4 OH. Except in 2-3 cases, don't bother about them. It is universal. 4 hydrogens, 4 OH. And 3 more oxygens distribute equally, and the 7th oxygen in the middle jointly distributed, shared by both. So, in fact, you don't have an oxygen single bond. You never have a direct bond between oxygen and oxygen. That was not needed also. That was not even needed. Therefore, but once again, you can't draw the structure and decide. So, what you do is, you go by the generalization. 7 oxygens minus 14. Hydrogen, in most cases, it is plus only, except with metals. You know, hydrogen is always plus 1. Only with metals it becomes, for example, NaH. I need not tell you. Sodium is Na plus 1, fixed, H is minus. MgH2. Here I need not emphasize. Magnesium plus 2, which is fixed, minus 2. So, plus 4, plus 10. Each phosphorus is getting plus 5. Okay. Therefore, no peroxy. No peroxy bond. What do you mean by peroxy bond? Oxygen single bond. Oxygen single bond. H4P2O7. H4P2O7. Like this. Now, you try to find out whether there is a peroxy bond in this or not. HClO4, does it have a peroxy bond? How to find? Is there any fixed element? 1A, 2A, fluorine? No. Therefore, give minus 2 to oxygen, minus 8, plus 1. Hydrogen, most cases plus 1. Chlorine, plus 7. And okay for chlorine. Chlorine can afford plus 7. Chlorine belongs to 7th group. Plus 7 is okay. Therefore, no peroxy once again. No peroxy bond. Oxygen single bond is not there. What about H3PO5? 5 oxygens, 5 into give minus 2. You deliberately give minus 2 to oxygen. If everybody says okay, oxygen remains minus 2. If somebody objects, oxygen becomes minus 1. Minus 10, plus 3, plus 7, and this plus 7 is impossible for phosphorus. Maximum is just plus 5. Plus 7, therefore, it contains peroxy bond. How many? 7 minus 5 by 2. Impossible is 7. The demand for electrons is 7, but oxygen can meet a demand of 5 only, maximum 5. So, 2. 1 peroxy bond. 1 peroxy bond. 7 minus 5 by 2. Impossible minus maximum by 2. 1 peroxy. H3PO5. How do you manage the structure? 1 phosphorus. You know 3 OH groups are there. Number of OH. Number of OH is equal to number of hydrogens present. And one of them is OOH and a double bond. Phosphorus should form only 5 bonds. So, phosphorus is losing 5 electrons plus 5. This oxygen is minus 1. This oxygen is minus 1. This oxygen is minus 1. Why? This oxygen is gaining electron from this phosphorus. This oxygen is gaining electrons from this hydrogen. and they are not gaining anything between them. Like that, how to find peroxy bond? There is a categorical, strict, fixed method. Nothing was taken to chance here. Everything we are using a procedure and finding. Now, P4. What do you know about P4? It is an elementary state. It is not combining with anyone. All four are phosphoruses. So, there may be one bond or two bonds or three bonds, but they are between, all of them are between phosphorus. So, P4, it's like this, the fourth phosphorus. Because you know each phosphorus should form three bonds. 1, 2, 3. 1, 2, 3. 1, 2, 3. Each phosphorus 1, 2, 3. But all are PP bonds. So, what is the covalency of phosphorus? Covalency, number of bonds, 2. Oxidation state, 0. Because all are phosphorus bonds which end in a draw. The bond, no one wins. Okay? Because equal opponents, phosphorus and phosphorus are equal opponents, P and P are equal opponents. And the bond between equal opponents, nobody wins, nobody loses. Covalence is equal to 2, oxidation state is equal to 0. S8, 8 sulfur atoms in one molecule. S8, you should write 8 sulfur atoms. So, and you also know when sulfur forms two bonds, it is left with two lone pairs, and two bond pairs and two lone pairs, each sulfur should have a V shape around it. If you have sulfur here, there is a V, the other two sulfurs should be in a V. Now you will see, you are seeing so many V's here, V shape, V shape, V. Around each sulfur there must be a V shape because of two bond pairs, two lone pairs. You have got a crown like structure or a puckered ring structure because each sulfur is forming two bonds and two lone pairs. Two bond pair, two lone pairs, V shape. Here also V. Around each sulfur the configuration is V. This is called a puckered ring structure, puckered damaged ring and or a crown structure. What is the covalency of sulfur here? Covalency. Each sulfur is forming two bonds to no effect, forming no doubt two bonds, but the two bonds, no, it's not winning an electron, it's not losing an electron. P4S8. What about Cl2? Cl, no win, no loss. Cl. So 0, 0. Neither losing nor winning, two chlorines. OF2. H2TiO4. Find the oxidation state of all elements in these following. H2TiO4. HNO4. H2SO5. O2F2. KMnO4. OF2. Who will decide? Fluorine will decide. 2 fluorines minus 2, oxygen is made to be plus 2. O2F2. 2 fluorines minus 2, each oxygen plus 2. 2 oxygens plus 2, each oxygen plus 1. 2 oxygens of course plus 2, each oxygen plus 1. And H2TiO4. What about H2TiO4? Minus 8 plus 2 plus 6. It is impossible for titanium because titanium belongs to 4th group, titanium belongs to 4B and 6 is impossible. Therefore, it contains a peroxy bond. It is called per-titanic acid, something with a per. H2SO5 minus 10 plus 2 plus 8, impossible, peroxy. HNO4 minus 8 plus 1 plus 7, impossible. Pernitric acid, peroxynitric acid. Pernitric acid or peroxynitric acid, it contains a peroxy bond. persulfuric acid, peroxysulfuric acid. So, in some molecules the sound per will be there, but they need not be peroxy. For example, you have KMnO4 minus 8, potassium fixed plus 1, manganese plus 7, okay. So, for manganese plus 7 there is no problem, manganese can take as high as plus 7. Therefore, this is potassium permanganate, potassium permanganate. So, there is a sound PER in this per, but it does not have a peroxy bond. Actually, here per means too many oxygens, too many, per. Per here stands for too many, KMnO4. K2Cr2O7, decide the chromium, minus 14, 2 potassiums fixed plus 2, plus 12, each chromium plus 6, okay, potassium dichromate. So, what is the oxidation state of chromium here? Plus 6. So, that is how we have to find oxidation state categorically. And MnCl2, here neither you have oxygen nor a fixed one. So, what will you do? Use your common sense. You know chlorine, the manganese is a metal, it can never be negative. Therefore, when chlorine takes minus, it can take minus 1 only, it has only one minimum. Therefore, MnCl2, what can you do? 2 chlorines minus 2 manganese plus 2. Okay. Manganese is not fixed, but we know that one of them has to be positive, one of them has to be negative. Chlorine is the negative one, and when chlorine takes, it can take only minus. Chlorine has only one negative, that is minus 2. Minus. Arsenic sulfide, As2S3. Once again, you do not have any fixed element, but this is a sulfide here between arsenic and sulfur. Arsenic is a half metal, sulfur is a non-metal. Who can be minus? Sulfur only can be minus. When sulfur is minus, it is generally minus 2. It is generally minus 2. Therefore, you take minus 2 for sulfur, minus 6 plus 6. Each sulfur minus 2, each arsenic plus 3. Arsenic plus 3. It is like arsenic oxide. It is similar to As2O3. So, whenever there is a question on As2S3 sulfide, you just talk about As2O3. You see oxygen in sulfur because they belong to the same group, As2O3. So, since oxygen is minus 2, sulfur also generally minus 2. Very rarely it is minus 1 in a compound called persulfide, persulfide. Because FeS2, this is ferrous persulfide. How to know? Generally, iron is either plus 2 or plus 3, ferrous or ferric iron. Usually, everybody knows iron either plus 2 or plus 3. Ever heard of a compound called FeCl4? You must have very often heard FeCl2, FeCl3, but FeCl4 is not heard of. Not heard of because you haven't heard about FeCl4 means it is not there. Sulfur usually, iron usually does not exhibit that. Ever heard of ZnCl3? No. Most of the time you must have heard ZnCl2 only. Therefore, why haven't you heard about ZnCl3? Because it is not there. Zinc does not show that oxidation state. So, FeS2, iron plus 2, 2 sulfurs minus 2, each sulfur minus 1. This is a persulfide, like peroxide, it is a persulfide. You should compare that to FeO2. FeO2 where Fe cannot be plus 4, oxygen will be peroxide, persulfide, something. So, use your common sense in other cases. So, but frequently asked questions will contain most common compounds, not uncommon compounds, molybdates, tungstates, you won't have them. You will have only main compounds only usually. So, we have discussed all those things that are common. So, oxide, superoxide, peroxide, and we are deciding whether somebody is a peroxide or not using a categorical principle, not by using haphazard manner. H2S2O8, do you have a peroxy bond in it? 8 oxygens minus 16, 2 hydrogens plus 2, 2 sulfurs plus 16, plus 14 rather, plus 14. Each sulfur is getting plus 7, so this is impossible. Therefore, this contains a peroxy bond. This molecule is called per-disulfuric acid, per-disulfuric acid. Like that, If you have a fixed oxidation state, he will decide. If you don't have a fixed oxidation state, you go and give -2 to oxygen, and if all others are happy, then it's okay. Okay, that's all about oxidation state. We will begin something new. Until now, we have discussed how to draw any structure, maximum covalency, hybridization, and shapes of molecules. Now, the next interesting area is polarity. Polarity and the consequences of polarity. Look here. Suppose there is a molecule called Cl2 in which 2 chlorine atoms are participating. 2 chlorine atoms. And you know only the last electron, that is 3s2, 3px2, 3py2, 3pz1, only this particular unpaired electron participates in bonding. That is the 17th electron of this chlorine atom and 17th electron of that chlorine atom. So, the 2 chlorine atoms will be revolving around both the nuclei. Look at the movement of my hand. The 2 chlorine atoms are moving uniformly. Uniformly in the sense they are spending equal amount of time around both the nuclei. That is 50% of the time here or 50% of the time here, you can say. Equal. So, this is equal distribution of charge. Equal distribution of charge. Equal distribution of charge. And equal distribution in terms of what? In terms of time spent by the electrons around each nucleus. If the electron spends 1 second there, the next second it will spend here, and the motion is almost uniform. Electrons are moving with uniform velocity, you can say. So, equal distribution of charge with respect to time. With respect to time. So, this is called a non-polar covalent bond. Non-polar covalent bond. That is, no atom between these two is more negatively charged than the other. Both are equally negatively charged because it is equal distribution of charge. And look at the molecule HCl. HCl. Look at hydrogen, chlorine. Between hydrogen and chlorine, we all know that chlorine is more electronegative. How to remember the order of electronegativity? Look here. F greater than O greater than N greater than Cl greater than hydrogen greater than boron, like this. So, fluorine is the most electronegative. So, this is electronegativity of fluorine greater than oxygen greater than nitrogen greater than chlorine. And you will get the other non-metals here. You know which are non-metals: bromine, iodine, sulfur, phosphorus, carbon, silicon. All others will be here. And after this boron, you will encounter half metals and metals. Half metals and metals. They are not electronegative, they are electropositive. So, what is happening here? Since 2 chlorines are equally strong in the sense they are equally electronegative. What is electronegativity? The tendency to attract the shared pair of electrons more towards oneself. Here the 2 electrons are spending equal time, but here the chlorine keeps electrons more towards itself. More in what sense? More in the sense that it attracts the electrons for a longer time. And look at the observe the movement of my hand. Look here. Electrons are moving rather slowly, and when they reach hydrogen they come back quickly. So, they are moving slowly here, slowly, and when they are going to hydrogen, so you can say they are spending 40% of time here, 60% of time. For example, this is not exact values, I am just giving a comparison. So, the two electrons, the two outermost electrons are spending more time around chlorine nucleus because it has 17 protons to hold the electrons, and hydrogen of course has only one proton. Therefore, this is called unequal distribution, and this is unequal distribution. This is called polar covalent bond. Polar. This is also covalent bond. This is also covalent bond, but that is a non-polar covalent bond, and this is a polar covalent bond. So, and observe HF. Fluorine is in fact the most electronegative. Therefore, it keeps the electrons more towards its row. The electrons will not leave fluorine at all. They stay a long time with fluorine and spend very few moments with hydrogen, fluorine. Unequal distribution, hydrogen, fluorine. Look here, the electrons are spending a lot of time here and very little time around hydrogen. So, they are spending a lot of time here and just hydrogen just they are making. So, you can say it is 30%, 70%. This is highly unequal distribution of charge. Highly unequal, this is highly polar covalent bond. And you won't have this highly polar covalent bonds in many molecules, only in molecules with FH, OH, NH bond. FH, OH, NH bond only. Very few cases, there may be one or two others, but we should always learn the broadest thing which is applicable for 99% of the cases. Let us not worry about a few others. FH, OH, NH only, and whenever there is a highly polar covalent bond, that is FH, OH, NH bond, that leads to what you call hydrogen bond, which we will discuss later. Hydrogen bond. So, hydrogen bond is present only when FH, OH, NH bond is present. Now, so we have already seen three cases of covalent bond: non-polar, just polar with some inequality, highly unequal, highly polar, which leads to hydrogen bond in the long run. Now, NaCl is indeed a very special case to discuss. NaCl. So, let me conclude. Cl, non-polar covalent bond, equal distribution of charge, 50%, 50%. HCl, polar covalent bond, polar covalent. HF, highly polar covalent bond, which is present only in molecules containing FH, OH, NH bonds only. FH, OH, NH bonds only. Now, NaCl is interesting case in point. The valence electron of sodium 3s1, if you remember, and the valence electron of unpaired electron of chlorine 3pz1, these two electrons, they are almost always around this chlorine, but it doesn't mean that they will never come back to sodium. They come back to sodium, but only for a short, very, very short time, say 20% of the time here, 80% of the time. This is very highly polar covalent bond, which we call as ionic bond. So, after all said and done, ionic bond is nothing but a very highly polar covalent bond, where we assume that the electron permanently is transferred to chlorine, and electron is a negative charge. It is not possible to charge transfer completely. However much you try, you may not be able to transfer the electron completely. Some of the charge will still be attracted towards this Na plus also. Depending on the charge transfer, the percentage of charge transfer, you can decide whether somebody is highly ionic or somebody is highly covalent or highly polar. Okay, this is it. So, classification, covalent bonds are 4 types. Covalent bonds. Non-polar, less polar. Less polar means polar. These are one variety of molecules. Non-polar molecules, less polar molecules, and highly polar. Highly polar molecules, FH, OH, NH bonds. NH. And very highly polar, as in the case of ionic bond. So, no bond is 100% ionic. Even in an ionic bond, there still is some covalent character. What is covalent character? Give and take. I will give you, but I still take it back. No bond is 100% ionic in nature. So, you can now classify, you have got 3 classifications. Highly polar, which leads to hydrogen bond, ionic bond. Now, how to say if a molecule is polar or not? SO2, is it polar or not? How do we know whether the bonds are equally distributed or unequally distributed? Therefore, there is a simple way to find out. Lone pair is present. In a molecule, if lone pair is present, then that is polar. If lone pair is present, polar. Of course, XeF2 and XeF4 are exceptions. The reason being, despite the presence of lone pairs, these two molecules have a symmetric structure. XeF2 is linear and XeF4 is square planar. Therefore, except these two, if a lone pair is present, it is polar. 2. No lone pair, but dissimilar terminal atoms. Dissimilar terminal surrounding atoms. Dissimilar terminal atoms. SO3, who are the terminal atoms? 3 oxygens. All 3 are oxygens, they are similar. But CHCl3, look at CHCl3. You have 1 hydrogen and 3 chlorines, they are not similar. So, whenever there is something dissimilar, that itself is polarity. Polarity means opposing nature. 2 poles, 2 opposite natures, opposing natures. Polarity means dissimilarity. Now, so CHCl3 is also polar. So, first 2 cases polar. So, when is a molecule polar? If a lone pair is present, definitely polar. There is no lone pair, but still the molecules are dissimilar. SOCl2, sulfur surrounded by 1 oxygen and 2 chlorines. One of them is an oxygen, 2 of them are chlorines. Therefore, obviously dissimilar, polar. 3. Third case, no lone pair, but no lone pair and similar terminal atoms. No lone pair and similar terminal atoms. All atoms are similar. Cl2, both chlorines are similar. P4, all of them are similar. No lone pair and similar terminal atoms. Then also this is non-polar. Now classify. I will just give a molecule. You just have to tell me 1, 2, 3. NH3. Lone pair is present. Lone pair is present, therefore it is polar. So, you should know whether a lone pair is present or not. That we discussed earlier, saying that NH3, nitrogen belongs to 5th group, 5 minus 3 by 2. I am once again reminding you of how to find lone pairs. So, this leads to The presence of lone pair leads to polarity, and the presence of lone pair itself leads to what you call that nature. 3, 1, pyramidal geometry. NH3 polar, 1. CO2, carbon dioxide, there is no lone pair, and both the oxygens, I mean both the terminal atoms are similar, therefore belongs to the third category, non-polar. SnCl2, lone pair, therefore lone pair is present. SO2Cl2, there is no lone pair, SO2Cl2. There is no lone pair, but non-polar. But polar. Why? Dissimilar terminal atoms. Dissimilar terminal. So, 2. Like this, using these 3 simple rules, in fact, there are only one rule you can say. Lone pair, no lone pair. That's all. Similarity, dissimilarity. Dissimilarity means that leads to non-polar. Now, between 2 molecules of HF, I am talking about molecules. Between 2 molecules of HF, what can exist when 2 molecules of HF are together? This fluorine is highly electronegative. Therefore, it always keeps a pair of electrons close towards itself. What is electronegativity? The tendency to attract shared pair of electrons more towards oneself. To keep the shared pair more towards me. Here these 2 electrons belong to both hydrogen and fluorine equally, but fluorine wants to enjoy a lion's share of it. Therefore, it always keeps the electrons. So, it becomes minus delta plus delta. And here this fluorine also minus plus. Actually, we are defining electronegativity very late, in the sense we saw the trends in electronegativity in periodic table itself. But why are we discussing now? Now only I will be able to discuss this, because it is about shared pair and shared pair being close to one atom. So, that's why earlier I did not even attempt to define, because in any case we are going to define today. The tendency to attract shared pair of electrons more towards oneself is called electronegativity, and because of electronegativity an atom becomes partially negative, minus delta, partial negative charge. So, between these 2 molecules, what happens is a strong force of attraction is developed. It is attraction between molecules. Until now we have been discussing attraction between atoms only. We are discussing the bonds inside an atom. Now we are discussing an attraction outside the atom. This is called hydrogen bond. Okay, this is called hydrogen bond. So, because of hydrogen bond, molecules are strongly attracted. HF, 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 there is strong force of attraction between molecules of HF plus delta minus delta. So, this is hydrogen bond. So, when compared to HCl and HCl, the attractions are very strong. Here also chlorine is minus, here also chlorine is minus, plus, minus, plus. There is attraction here also. So, chlorine is definitely more electronegative, minus delta, plus delta. You have attraction here also, but the attraction is not strong enough to be called a bond, mind you. You can't call this a bond. Okay. So, a person whom I have met for 2-3 days, I can't say he is my friend. I can only say I have familiarity with him, I know him. Friend means the attraction should be strong enough. This is hydrogen bond. You can't call this, you definitely can't call this hydrogen bond. That's why I strictly tell, when can you say hydrogen bond? When you have oxygen here or when you have nitrogen here. So, this can be called dipole-dipole interaction. Dipole-dipole interaction. Just familiarity. HCl and HCl know each other. They are not good friends. Okay. dipole interaction. So, why is it called a dipole? Two poles, two opposite charges like north pole and a south pole, dipole, plus and minus are also two different poles, dipole interaction. So, same phenomenon of electronegativity, same phenomenon of partial charges, same attraction between opposing charges, but depending on the strength we are calling it hydrogen bond and we are not calling it hydrogen bond. For you to call it a bond, it should have a minimum some bond energy there. So, what happens as a result? When HF is in liquid state, HF liquid state and HCl is in liquid state. Imagine they both are gases at room temperature, but imagine them in their liquid state. So, when two HF are in liquid state, there is strong force of attraction between molecules of HF. Molecules of HCl, there is less force. So, when you heat, what happens? When you heat, it is easy to overcome this attraction, these cohesive forces, because they are not strongly bonded. It is easy to overcome the force of attraction. Therefore, HCl goes to vapor state easily. HCl liquid to HCl gas, it is easier when compared to HF liquid to HF gas, it is relatively difficult. Therefore, the boiling point of hydrogen fluoride is more than that of HCl. So, boiling points depend on intermolecular forces, whatever is there between two molecules. Don't look at whatever is between two atoms, because while boiling, what is that you are doing? You are just separating the molecules and taking them to a different state. You are not damaging the molecule. You are not breaking this HF bond. HF in liquid state, this is HF. This is breaking HF. Let this be hydrogen, let this be fluorine. This is HF. This is HF. So, doing this means breaking HF bond. Doing this means breaking HF bond. But what is it I am doing? Two molecules in liquid state, I am just separating them. So, this is still HF, this is still HF molecule. So, I don't look at this bond, always look at this only, this attraction. So, this is called dissociation. Breaking the bond is dissociation. Breaking the bond between molecules is boiling. So, boiling points depend on intermolecular forces, which are called cohesive forces. Now, so how to decide boiling points of all substances? Look here. There are so many factors like boiling point, critical temperature, which you learn in different topics, ease of liquefaction, how easily you can liquefy somebody, So, ease of liquefaction, ease of adsorption, there are many things which are directly proportional to intermolecular forces of attraction. Here, I can't define critical temperature, we are unnecessarily deviating from our main point, but definitely boiling point and ease of liquefaction, liquefying, bringing the molecules together and separating them together. To bring the molecules together, they want to come together to start with. If only they want to come together, you can bring them together. So, they want to come together when there are some attractions between them. So, therefore, greater the intermolecular forces, it will be easier to liquefy and difficult to boil. Boiling will become difficult rather. So, all these things, okay. Intermolecular forces, we can classify intermolecular forces. Intermolecular force of attraction. We have metals which is called metallic attractions. In metals, we have metallic attractions, and the bond existing there is called metallic bond. Here, when I said intermolecular, I mean it is intermolecular, interatomic, interionic, interspecies attraction, any species, be it molecule, atom or ion. So, metallic bond and very highly polar substances. What are very highly polar covalent substances? As we were defining, very highly polar covalent substances are ionic compounds. Ionic compounds. In ionic compounds, the attractions are very, very highly polar in nature. Now, ionic compounds, and the bond is called ionic bond. Ionic bond and highly polar attractions. Highly polar attractions, which is called hydrogen bond, and you will find hydrogen bond only when H, OH and H are there. And the last one being less polar or non-polar. Less polar and non-polar molecules, there can be several types of attractions, all other than ionic bond, other than metallic bond, other than hydrogen bond, other than these 3 bonds, all other attractions are called van der Waals attractions. A few moments ago we discussed dipole-dipole interaction, ion-dipole interaction, dipole-induced dipole interactions, induced dipole interactions, London forces, dispersion forces. There you give any name. If it is not a metallic bond, and if it is not an ionic bond, and if it is not a hydrogen bond, all others are van der Waals. And this van der Waals force of attraction is directly proportional to atomic weight or molecular weight. Atomic weight or molecular weight. Okay? Therefore, boiling points in general, and I warn you, whether we write this or not, behind every statement in chemistry, you should always think in general. There can always be exceptions, and ours is not a job to worry about exceptions. Learn the large, broader spectrum, 99%. In general, metallic bonds are stronger than ionic, stronger than hydrogen bond, stronger than van der Waals. I am not saying there can be ionic bonds which are stronger than metallic bonds also. Some ionic compounds, the attractions are so strong that even they are stronger than metals. So this is not a permanent one, in broadly. So when you are given 4 substances, how to compare their boiling points, you should see whether it is a metal or not. I ask you this question. HCl, what is this bond? Is it ionic or covalent? Ionic or covalent? How can we say? Listen, there is only one way. HCl, no metal, no ionic. When you don't have a metal, it is not ionic, that's all. No metal, no ionic. I don't guarantee if a metal is there, it is ionic. But if there is no metal, no ionic. Now, tungsten, NaCl, HF, methane. Which among the following is likely to have the highest boiling point? Tungsten is a metal. Therefore, in general, metals have high boiling points. NaCl is an ionic compound. Ionic compounds of boiling points, melting points, they are higher than. And between HF and CH4, HF is more because in HF you have what you call hydrogen bond, highly polar attractions, but in methane you don't have anything. In methane, if you observe methane, between 2 molecules of methane, what force exists? A methane and another methane. What is the force existing here? If they are tungsten atom, the attraction will be metallic. Between tungsten, metallic. Between NaCl and NaCl, it is ionic. Between HF and HF, you have at least have hydrogen bond. But what do you have here? Nothing. You don't have any attractive force between methane and methane, and that nothing is called van der Waals force of attraction, which depends on mass. Van der Waals force of attraction. Now, tungsten, NaCl, HF, methane. So, if you are asked to compare the boiling points of same sets of elements, look here. Helium, neon, argon, krypton. Boiling points of. How to compare the boiling points? Helium, neon, argon, krypton. Are they metals? No. How to classify metals? How to find out which are metals? Very simple. All sounds ending in N. Helium, sulfur, phosphorus. These are non-metals. All sounds ending in N, like fluorine, chlorine, bromine, iodine, oxygen, sulfur, like that. Nitrogen, phosphorus, boron, carbon, silicon. All sounds ending in N, helium, sulfur, phosphorus are non-metals. Germanium, arsenic, antimony, selenium, tellurium. These are half metals, and all others are metals. Just remember this. Sounds ending in N, helium, neon, argon, krypton, xenon, radon. All of them are ending in N. Fluorine, chlorine, bromine, iodine. Oxygen, sulfur. Nitrogen, phosphorus. Carbon, silicon, boron, hydrogen. Except these three, all non-metals have N. So, all non-metals, all names ending in the sound N, helium, sulfur, phosphorus are non-metals. Germanium, arsenic, antimony, selenium, tellurium, half metals, and all others are metals, as simple as it. So, if I ask you, are they metals? No, they are non-metals. They are non-metals. So, is there any ionic bond? They are not even compounds. Is there any hydrogen bond? Hydrogen bond is there only in compounds between two molecules. So, what you should look at is only the mass. So, boiling point of helium is less than that of neon, because boiling points, in this case, boiling points, I repeat, in this case are directly proportional to atomic weights. Not in every case they are directly proportional, only in this case they are directly atomic weight, because there is nothing else to distinguish between helium and helium, neon and neon. There is nothing else. What exists between two atoms of helium and two atoms of neon? Nothing. That nothing, of course, is called van der Waals. Helium, neon, neon. There is no force of attraction, and only you have to rely on the mass, van der Waals force of attraction. Now, fluorine, chlorine, bromine, iodine. F2, Cl2, Br2, I2. So, I am always ruling out the possibilities. Are they metals? I am seeing whether they are metals, whether they are ionic compounds, whether they have hydrogen bonded compounds, or van der Waals. So, are they metals? Not at all. Fluorine, chlorine, they are not metals. Are they ionic compounds? They are not even compounds, they are elements. Do you have hydrogen bond? There is not even a hydrogen there. Therefore, so first three are ruled out. Now, what is it you should rely on? Only mass. Between two molecules of fluorine and between two molecules of chlorine, what exists is nothing but mass, van der Waals force, and in chlorine it is more. Therefore, boiling point of fluorine, so it is easier to separate molecules of fluorine rather than chlorine. Fluorine, chlorine, bromine, iodine. Boiling points of. That is why fluorine and chlorine are gases at room temperature, bromine is a liquid, iodine is a solid. Okay? Greater the intermolecular forces, molecules come together. When they come together, it is called liquid. What is a liquid? Where the molecules are very close. Solid means molecules are very close. Liquid, gas, very far away. Solid, liquid, gas. So, here the molecules are very close because of intermolecular attractions, and iodine still greater intermolecular attraction, therefore it is a solid. Now, HCl, HBr, HI. Once again, same logic. Are they metals? No. Are they ionic compounds? No. How can you say no metal, no ionic? HCl, is it ionic or covalent? I can say it's covalent because there is no metal. I am not saying if a metal is present, I don't guarantee it's an ionic bond. Suppose if you ask me whether AgCl is ionic or covalent, perhaps I can't say. AgCl, is it ionic or covalent? I can only compare. I can only say that AgCl is more ionic than AgBr. AgCl is more ionic than AgBr and less ionic than AgF. But I strictly can't brand it as an ionic compound. Okay? When it comes to ionic, you can't strictly brand somebody as an ionic compound. You can call somebody as more ionic, somebody as less ionic, but no one can be branded like that. So, but covalent compounds, definitely they can be branded. No metal, no ionic, it's a covalent. So, do you have hydrogen bond? Hydrogen bond is there only when fluorine, oxygen, okay, nitrogen. Therefore, only mass now, HCl, HBr, HI. Between HCl and HCl, HCl and HCl, HBr, HCl, this is lesser. Now, 3. Like this, you can compare any sets. 4. H2O, H2S, H2Se, H2T. H2T. What happens? Or once again, are they metals? No. Are they ionic compounds? No. Are they hydrogen bonded? Yes. H2O has hydrogen bond. If you answer carelessly, this will be the order. Boiling point of, you will be writing like this, boiling point, but H2O, no. Why have I written H2O here? Because of its mass I have written here, lesser mass, but H2O, the boiling point is highest because of hydrogen bond. Because of hydrogen bond. So, that is in a systematic way, you have to verify things. So, you should not answer in a haphazard manner. Boiling points, there is a principle. Follow the principle and apply that. Okay. Don't need to memorize anything. How to find which has more boiling point? You will definitely don't memorize anything. Hydrogen bond. With all others, H2S, nothing exists between two molecules of H2S and H2S. Weak force, weak van der Waals force exists and nothing else. 5. So, in the group ammonia, NH3, PH3, ASH3, SbH3, if you observe closely, what I am comparing are the boiling points of hydrates of non-metals. A study we have to make in the P block. All these are hydrates. Hydrates of 6th group, oxygen, sulfur, selenium, tellurium, nitrogen, phosphorus, arsenic, antimony. So, compounds formed by hydrogen and compounds of, elements of 5th group, 6th group, 7th group. So, once again they depend on intermolecular forces. Intermolecular forces depend on whether they have hydrogen bond or not, whether they have ionic bond or not. So, NH3 should have been less. It should have been less because of its lesser molecular weight. If you consider molecular weight only, no. But ammonia comes only second in this list. It doesn't overtake stibine. Okay. Though it has hydrogen bond, it could not surpass stibine. NH3, SbH3. Next, boiling points of, once again, methane, silane, germane, stannane. Mass only, because they are not metals, they are not ionic compounds, they are not hydrogen bonded. Therefore, we are relying solely on their mass. Methane less than, silane less than, germane less than, stannane. Next, methane, ethane, propane, butane. The first 4 alkanes. How to compare? between methane and methane and ethane and ethane. Methane, methane, ethane, ethane. What exists? Nothing. Nothing except van der Waals. Therefore, only mass. Greater the mass, greater the molecular weight, greater the. And a last instruction is this. Among isomers, where you don't even have mass to decide, isomers will have the same mass. Isomers means same molecular weight. So, among isomers, what will happen is more branches, less van der Waals force of attraction. Whatever be the reason, let us not go into those details. Less van der Waals, less boiling point. Among isomers, more branches, less boiling point. So, you have N-pentane, isopentane, neopentane. N-pentane, there is no branch. Isopentane means one branch. Isopentane will have, this is isopentane and this is neopentane. 5 carbons, but still 2 or like this. This is, therefore, more branches, less boiling point. So, this is normal. That's it. So, this is used as a last tiebreaker. Talking about surface areas and their dependence on boiling point, that is the last resort. You look at it when there is no other force of attraction exists actually. Between orthonitrophenol, this is called orthonitrophenol. This is benzene. If you have a OH and benzene, it is called phenol, and you have NO2 next to OH, it is called orthonitrophenol. And paranitrophenol, the same phenol, but the NO2 is in the para position, opposite to it. This is called paranitrophenol. Look here. Whose boiling point is more? Both of them have same formula, both of them have same molecular weight, but here you have attraction between these two molecules, H plus delta and O minus delta. This is called intramolecular hydrogen bond. Intramolecular hydrogen bond. Intra, within the same molecule. So, this is nothing special. You have a coordinate covalent bond here, a pi bond here, 3 pi bonds here, so many sigma bonds. So, this is just one other bond. You have so many bonds and this is one among the many bonds, and because of that nothing special happens. So, what exists between orthonitrophenol and orthonitrophenol? Virtually nothing. Orthonitrophenol, there is no force between two molecules. I repeat, I am interested in attractions between one molecule and the other, but this is intramolecular attraction that doesn't bring about much change. But in the case of paranitrophenol, the intramolecular hydrogen bonding is possible, NO2. You take another molecule of OH. Since this hydrogen is free, plus delta, minus delta, look here. Earlier NO2 was here, therefore it was intra, this is intermolecular hydrogen bond. Boiling points depend on whatever is there between two molecules, not what is there inside that molecule. So, intra doesn't affect hydrogen bonds, only inter affects, intermolecular hydrogen bond only affects hydrogen bonds. Therefore, the boiling point of para-nitrophenol is greater than that of para-nitrophenol greater than that of ortho-nitrophenol because of intermolecular hydrogen bond. Here whatever you have, it is intra. So whatever is within will not bring any change to the cohesive forces, intermolecular forces. And therefore you say ortho-nitrophenol is volatile, more volatile means boils more easily. Which boils more easily? Where the forces of attraction between molecules are not very high. And as a result of this polarity, this becomes minus delta and this becomes plus delta. So as a result of polarity, and there is an electrostatic force of attraction between these two. Electrostatic force of attraction. Whenever there is a force multiplied by distance, a moment is developed. Moment. So moment of forces, which is called dipole moment. What do you mean moment? Force into distance from where the force is acting. Here is a positive charge and here is a negative charge. Some force is acting between them, and how far is that acting from, and that decides dipole moment of the molecule. Dipole moment is equal to mu. Dipole moment mu is equal to charge acquired by each molecule, whether it is positive or negative charge, into distance. Charge into distance, which is called bond length. Bond length. Charge into bond length. So charge has 10 power minus 10 is of the order 10 power minus 10 electrostatic units. Charge is of the order, means it is 4.8 into 10 power minus 10. I am just taking that 4.8 into 10 power minus 10 electrostatic units. And bond lengths are usually measured in angstrom. They are of the order 10 power minus 8 centimeters. 10 power minus 8. It can be 1 angstrom, 2 angstrom, 1.4 angstrom, depending on the bond length. But angstrom means 10 power minus 8 centimeters. Charge that can be transferred maybe 1 electron, 2 electron, half an electron. It can be anything. Though you believe electron is the simplest amount of charge that can be transferred, when I use the word half an electron, what I mean? Electron is given only 50% of the time. Electron is given, but only for 50% of the time, which makes it half an electron technically. So since charge is of this order 10 power minus 10 and this is 10 power minus 10, multiplied you get 10 power minus 10, 18 electrostatic unit centimeters. 10 power minus 18 electrostatic unit centimeters, and this is called 1 d by d, the symbol. So what is dipole moment? Charge acquired by any one of the atoms, be it positive charge or negative charge. I am not interested in the sign, I am only interested in the magnitude. So you just consider the magnitude of positive charge, negative charge, which are equal, charge acquired by any one of them, and bond length. And it is you measured in d by, 1 d by is equal to 10 power minus 18 electrostatic unit centimeters. So that's it. Suppose a molecule is non-polar. What does that mean? Molecule is non-polar. Non-polar means polarity of the molecule is 0. So its dipole moment is said to be 0. Non-polar, no polarity. Look here. Here is an interesting case in point. BeCl2. Here the bond between beryllium and chlorine is a polar covalent bond. Why is it polar? Because it is between two different atoms, beryllium and chlorine, polar. It is a polar covalent bond. This is also a polar covalent bond. Means the bonds are polar, but the molecule as a whole is a non-polar molecule. Non-polar molecule. Carefully observe. Polar bond, but molecule as a whole. So there are differences inside. There are difference of opinion between beryllium and chlorine, beryllium, chlorine. But as a molecule, as a whole, it is calm, because the dipole moments cancel each other. Whatever the dipole moment which is acting in this direction towards the greater electronegative, they cancel each other. So there is polarity in the bond, polar covalent bond. I and you should be careful. Polar covalent bond. This is non-polar molecule. ठीक है ना? A molecule with a polar covalent bond, but non-polar polar bonds, non-polar molecule. Okay, there, that's it. When the forces do not cancel, okay, SnCl Cl, that BeCl2 molecule was linear. Therefore, the two forces are acting in equal and opposite directions. Therefore, 0. Here, look at the direction of this charge SnCl2. This way, they don't cancel, and you know the resultants and vectors and all that. That's not necessary here. If you closely observe the syllabus, JEE syllabus, you look at the syllabus, dipole moments, qualitative aspects only. Qualitative aspects only means no calculations based on this. You should not do any vector addition, or you should not apply any physics here or maths here. Okay? Qualitative aspect, look at the syllabus. JEE has a prescribed syllabus, and look at the syllabus very, very, very carefully. Very, very important. We should not study blindly. If you want to study, there can be a million other things, but it's not possible. Chemistry syllabus, there are so many exclusions. Observe them carefully. This particular thing is excluded. Industrial details in metallurgy are excluded. So don't just study like a blind person. Open the syllabus. So dipole moments, qualitative aspects only. If you want to calculate, this is x, this is x, this is theta, and you are trying to calculate the resultant, mu is equal to, using that mu is equal to square root of mu1 square plus mu2 square and all that. This is not required, and if that is necessary, you can do it very easily. In any case, physics, that is no big thing. In chemistry, when it is introduced for the first time, it may appear very strange and very interesting, but that is not necessary in chemistry. Dipole moments, qualitative aspects only. Which is more polar? So dipole moment of HCl, HBr, HI. Dipole moment mu. Dipole moment. HCl definitely greater than, because more electronegative. Greater the electronegativity, greater the dipole moment. Greater the electronegative difference, greater the dipole moment. Chlorine is more electronegative, therefore it holds the electrons more close towards its than dipole. HF greater than HCl, like that. So you can easily compare bonds. Boron trifluoride. Once again, the bonds are polar. Boron fluorine bond is highly polar, but because it is a symmetric molecule, planar molecule, symmetric, the net dipole moment is 0. Bond moments exist, but the molecular moments don't. Molecule as a whole is non-polar. So polar bond, polar inside, non-polar outside. This is better. Polar inside, non-polar outside. What about ClCl? This is non-polar inside, outside as well. Non-polar inside, non-polar outside.